Our next speaker today, Dr. Kara Webster, a forest soil ecologist with the Soil and Water Sustainability Team at the Great Lakes Forestry Center in Sault Ste. Marie. She investigates carbon and nutrient cycling in forest and peatland soils to improve policies for forest sustainability in a changing climate. And if that's not cutting edge, I don't know what else would be. Her research interests are focused on understanding the microbial, physical, and chemical controls on the fate of forest soil carbon. Dr. Webster combines field monitoring, imperial and ecosystem modeling, and GIS mapping to investigate soil processes across various spatial scales from plot to landscape. She has a BSc in ecology from the University of Guelph, an MSc in ecology from the University of Calgary, and a PhD in biology and environmental science from Western. With that, Dr. Webster.
Thank you very much. Thank you for inviting me here today. It's a pleasure to be here. So the project that I was funded for was digital soil mapping and for eFRI in Ontario's diverse landscapes. And you'll see from my the title slide here that we have some people from MNRF, Dave Morris, which is in the room here today, Peter Ulig, and some other co-PIs from CFS as well, Ken Baldwin, that deals with the Canadian Forest Ecosystem Classification System, Rob Fleming. There's also two other names on there. They were postdocs on the project. I've decided that I'm going to advertise that if you come work for me, you'll get a permanent job at a university. I've started out thinking I would have one postdoc throughout this whole entire process. And the first one, Clement, started some of the background work, got offered a full-time tenure-track position at Tennessee State. And then I found the other perfect candidate to take over from him and do some of the mapping stuff. And he just got a tenure-track position at Dalhousie University. So I have now found a third postdoc. And he also looks excellent, and I'm just hoping that I can make it through to the rest of the end of the project without having to replace him. So if you're looking for a permanent job at a university, come work with me. It's guaranteed. Anyways, so the whole premise of this is soils are important, and I had this talk with the taxi driver this morning going to the airport. He was asking me what I was doing, and I explained, how I work in soils, and I said, soils are a very undervalued resource that we have, and he agreed with me, so I felt good about that. But, we often take them for granted, partly because we don't see them. We step over them all the time, but we don't realize that there are so many valuable ecosystem services that are attached with soils. It's highly sought after information to have soils data. And not just for forestry-related applications. You can see from the, my little diagram here that, we need it to understand water quality and quantity. We need it for carbon accounting at across scales. Important for biodiversity, habitats, non-timber forest products. A lot of different users need to know about the distribution of soils. And soils are a product of many different factors, and this is called the CLORPed approach. So that refers to climate. So the CL is climate, O is organisms, R is relief or topography, P is parent material, and T is time. So if you look at the right-hand side there, what you have as a current soil is a product of, first of all, the parent material that was there, and obviously over time that erodes and weathers, and that weathering is a function of the climate of the area, which affects rates of weathering. But organisms are also very important, and that's not only the trees that grow above the soil and are inputting litter into the system, but also the microorganisms that are decomposing and doing all sorts of mineralization within the soil. Relief or topography is a really important driver of soil formation in terms of transport of water and nutrients, particulate matter downslope. And the most forgotten soil forming factor is probably time. Just have to remember that all of this takes a while to happen. Soils are a very long process to develop. So in part because of all those complicated factors that determine what soil is there, they're very challenging to map. Existing maps are usually quite coarse. There's the problem that they're not easily remote sensed because they're covered up with vegetation and litter layers and etc. So the other thing is that typically soil surveys have been done, but they're very expensive to do and they're typically very subjective in terms of what they're looking at. They're not necessarily predicting properties, but predicting soil types, which may not be useful to a lot of users. And typically, their soils are inferred then from their landscape position and vegetation associations and not from the direct drivers of it. The problem is particularly acute in northern Ontario. You can see in this map here of soil survey coverage that obviously the southern Ontario where there's a lot of agriculture, or even in northern Ontario where there's some agricultural areas, that's where you'll see soil survey data. But for the rest of the area, there is not much available in terms of soils. So one potential solution to this problem of needing soil data, which everybody is interested in having, is digital soil mapping. And digital soil mapping has become possible more recently, and I'd say the last 20 to 30 years, in part because of the increase in computing power that we have with computers. Plus we also have a whole range of spatial layers that are now available to us. And also there's been an increase in the statistical techniques that we can use in order to deal with large data sets as well. So digital soil mapping essentially uses that, what I refer to as the CLORPed approach, and brings together all sorts of soil information, that the drivers of soils. So it will bring together climate layers, land use and land cover layers, digital elevation model attributes, and the superficial and bedrock geology layers. And there's been a lot of work done in digital soil mapping, but most of it has been more at local scale. So it's been successfully applied at local scales, but there's a lot of challenges in applying it at broader regional scales. So the goal of this project was to develop a strategy for digital soil mapping that could be used consistently across Ontario, but also taking into account that the geography of Ontario is not homogeneous, that we have a variety of different landscape types. And so in part to develop a toolbox that we could apply and identify the key knowledge and data gaps that would prevent us from implementing it. So as part of my proposal, I put together this really nice Gantt chart. I like Gantt charts. They're very pretty. It separated the project into two phases, a phase one and a phase two. Essentially, phase one was more getting the background information that we needed. Phase two was the more applying the data into the mapping. But life always throws you some curves. And my husband and I ended up adopting a child in December 2015. Yeah, December 2015. It's hard to remember the dates anymore. So that kind of altered my schedule a bit. I took parental leave with her. But then a surprise happened, and we ended up with another child as well. So shortly after taking my first leave, I became pregnant and had a daughter in October of 2016. So I'm very thankful to Forestry Futures for being very patient with me as I tried to figure out my new life and dealing with staff turnover issues in terms of everybody I hire seemed to find a good job at the university. So I just threw the Gantt chart out the window. So anyways, I'm going to go through some of the steps that we've accomplished so far. The whole project is not complete at this time. We are now complete the first phase in terms of all the background information, so I'll go through some of the products that we've gotten from that. And then we do have some initial mapping products that I'll show you at the end. So the first part of this was to do an annotated bibliography, just to sort of get a baseline of sort of documenting the major advances in digital soil mapping, specifically related to forest systems. So there's been a lot of digital soil mapping done more for agricultural purposes. That in the literature for forests is a lot more limited. So we came up with 78 papers, 25 of which were related to Canadian examples. And we focused primarily in the last 10 to 15 years. And you can see that, as I said, that the rise in data availability, computing, and statistical techniques, you can see that there's been a rise in the number of studies that have been done. A little bit of a decline in the last five years or so. So as part of that review, and that annotated bibliography is now done. If anybody has interest in receiving that, I'd be willing to share that. But as part of that review, we wanted to take a look at what are some of the approaches that are used for digital soil mapping. And these are the major ones that you can find. So geostatistical approaches, which are strictly look at, if you're closer in terms of space to one point as to another, then you're more likely to have similar characteristics. The second type of approaches are what I refer to as the CLORPT approaches, that essentially you have environmental covariates. And the way that you can combine those predictor variables in order to get to look at responses can come in many different ways. They can be sort of linear models, like GLMs or GAMs, or multiple linear regression. It's sort of the most simple one. You can get into different machine learning approaches, and then expert knowledge or fuzzy inference type systems. And then finally, the last type of approach would be mixing some of those. So mixing the geostatistical with more of the CLORPT approaches. So those are sort of the main tools that you would have in your toolbox as a digital soil mapper. So just to expand a little bit more on the machine learning approach. So if you're not familiar with machine learning, it's essentially a process of uncovering patterns for large data sets that uses automated or semi-automated statistical models. And so this was sort of the approach that we've decided to take. There are many different types of machine learners, from tree-based learners. These are sort of like the classification and regression trees where you get splits in data and they progressively go out to final nodes. Those are really good for looking at non-linearities in your data, or hierarchical processes, which is quite appropriate for soils. Then there's other types of things, logistic regressions, logistic model trees. I'm not going to get into all of these. If you're really interested in some of the details, there's a couple of good review papers, including one by our Brandon Hung, who was the second postdoc on this project. He has a really good review of those in one of his papers, goes through and describes them. But so yes, we have logistic regression, logistic model trees, distance-based learners artificial neural networks, support vectors. So, I mean, it's quite amazing when you think of all the different types of machine learning algorithms that are out there. So one of the things that we noticed in the literature review was that a lot of people just took one single approach, assumed it was the best, and sort of went with it. And we were a bit worried that when we were dealing with Ontario with sort of very different landscapes, that one approach might work well in one area, but not work well in another area. So we decided to go with an ensemble approach, which essentially means running all of them and then looking at which of them did the best in doing the prediction. So that was the approach that we took. So yeah, going back to this idea that maybe where you are in the landscape, whether you're in the Shield or the Hudson's Bay Lowlands or on Great Lakes St. Lawrence or in true boreal forest, might affect what type of digital soil mapping might be the best. So we used the approach of using eco-districts as a way of segmenting the landscape in order to do the analysis. So in terms of different predictor variables, these are different layers that you could use in your digital soil mapping. So this is sort of reviewing what I've already said before. Climate could be important. Now, if we were to do mapping all across the province, climate might be really key to include. When you're looking at smaller areas that it's maybe not necessary to include broader climate gradients. Geology, as I mentioned before, superficial and bedrock geology could be very important in terms of determining that parent material that is underneath the soils. And vegetation in terms of, here is the Ontario land cover map. Now I want to talk a little bit about terrain variables here. I'm happy to see that LiDAR DEM is maybe on the radar here for eFRI because terrain variables are one of the most important things in terms of using as predictors for digital soil mapping. And it's not just simply elevation. You can have all sorts of primary and secondary terrain derivatives that you can use as predictors for soil. So, you have your basic Z, which is the elevation, but there's also, slope, aspect, curvatures, and then you can do more compound terrain derivatives, wetness index, sediment transport capacity index, and I mean, this list is not exhaustive by any stretch of the imagination. And then you can do more creative things like use stochastic depression analysis to delineate wetlands, landform classifications. There's all sorts of interesting things you can do with that terrain data to create sort of secondary attributes. And this is a bit out of date, but it's probably not too far out of date in terms of the current LiDAR coverage that we have in Ontario. It's pretty limited. So I'm happy to hear that moving forward that eFRI will include a LiDAR DEM layer because I think it's definitely one of the factors that is going to prevent more digital soil mapping across the province. So those are all the environmental covariates that you could put into these models, but just to talk a little bit about what it is we want to look at, what's the response that we're going to measure. And so there's all sorts of different physical, chemical, or biological properties of soils that we might be interested in predicting depending on what type of questions you're interested in. I've worked a lot in terms of predicting biological and chemical properties, but from the eFRI perspective, a lot of the information that they need is more on the physical properties like texture, moisture, and depth. And so that's where we've focused the initial part of our modeling is on these physical characteristics here. Now, of course, you can also have continuous versus categorical variables as well. And right now, in some ways, it's a little bit easier to do categorical variables, and these three are all categorical variables that we're looking at right now. But that's just to say that there's a lot more that you could do. There's more than just physical attributes you could predict. There's all sorts of other things you could do. And into the future, I'd like to look more at the chemical side of that. I think there's a huge need, particularly in this era of carbon accounting, to particularly be predicting carbon in the soils. So in terms of the inventory of the base data, this was a key part of our phase 1 planning. So we have eFRI data sets, we have growth and yield data sets, ELC plots, and also data from independent research groups as well. And so you can see here I've delineated sort of the key information that each one of these has and the coverage. So if we're looking to do this across the province, we need something that's done at a fairly high density, fairly consistently everywhere. And so these are the data that we came up as sort of the best types of data that we could use for this project. So it's important to consider not only the coverage, but the resolution and the suitability in terms of their accuracy. So the last part of phase 1 was to come up with some test areas. And so what we did was we used the eco-district map, and then we overlaid some of the LiDAR coverage for those different eco-districts. And we came up with three key test areas, 2 in this Boreal East and 1 in the Great Lakes St. Lawrence. So this is Hearst, Romeo Millette, and this is Petawawa Research Forest. We're likely going to add a fourth one in the Turkey Lakes area, watershed area, as well as the southern portion of the Romeo Millette Forest. I think would be another nice good example where we have contrast Boreal versus the Great Lakes St. Lawrence. And each of these, there's sort of a high relief and a low relief landscape within those. So those are the test areas that we selected. So the next major phase that occurred this summer was we hired someone to help send out emails to everybody that's involved in these wonderful data sets and get all of the data for each of these areas. And you can see that, for example, in the Hearst area, there's a lot of point data there. So that was, these are very valuable data sets that we have, and it was wonderful that we were able to get access to them for this project. So we're just starting the beginning of phase 2, so what I'm presenting today is sort of hot off the press, some of the first maps that we have for our first study area. So we started with the Hearst region as our first study area. Now, I went through that whole nice spiel about how to use an ensemble approach where you use many different methods and then choose the best from it. But today I'm just going to show you the results from one of those machine learning approaches, which is random forests. And the predictor variables we used were the surficial and bedrock geology and topographic indices from a 10-meter LiDAR DEM. And in total, there were 25 different topographic variables that were included there. So in this first run, we didn't actually have the land cover map, so vegetation is actually not part of these set of maps that you'll see coming up. The response variables were the moisture regime, 9 classes, depth to models, 7 classes, and texture, which was 42 classes. So we used the random forest. So random forest is a tree-based machine learner. And for you that are familiar with classification and regression tree, it in of itself is actually an ensemble method because it uses a bootstrapping approach to actually create many. So there's not just one tree as an output. It actually generates 1,000 different trees. So it in of itself is an ensemble method. And one of the benefits of doing this is, first of all, it allows us to create error surfaces. So because it's more of a probability, gives us a probability surface as opposed to just one strict answer. So I'm just going to take you through some of the maps that we created from here. So this first map is moisture regime. So what we see here is this is just an inset of this area right here. This up here is the classification uncertainty. So the redder is higher uncertainty, the bluer is less uncertainty. And then on the bottom here are two maps for two different moisture regimes. Moisture regime 3 and 8. And that is the class probability. So the higher the probability of a single pixel being in that category would be a red. So if you were definitely a moisture regime 3, you would be a red. If you were definitely not a moisture regime 3, you would be a blue. So one of the nice things of this random forest approach is that you can get more of these uncertainties. And so what was done for the validation for this was 70% of the data was used to train, 30% was used to validate afterwards. But this was done 50 times, so this allows us to get this map uncertainty part of the equation here. So you'll notice, and my question to Brandon, who did these wonderful maps for me, was I said, wow, there looks like there's a lot of uncertainty in low probability, class probabilities, even though we have an overall accuracy of about 77%. And you'll notice that this is pretty amazing. Over 10,000 field observations went into this map. So part of this reason why there seems to be this discrepancy between the class and overall accuracy, the uncertainty versus the accuracy is related to the point data. So we don't have predictor variables. So because each of these was one single point, there's always an uncertainty in terms of that one point within the 10 meters. So if you had a surface, so you'd had like a soil survey where you had a polygon over a larger area, he explained to me that the accuracies within the map would actually be higher. So I'm not sure I completely understand what he told me about that, but this is something I think we need to continue to work on. And like I said, this actually didn't include the vegetation part of this, and I think that would help to improve this. The next map is the modeling depth, so that would be sort of the seasonal high water table depth. And again, you can sort of see similar, there's a similar approach here. There's the inset with the classification uncertainty, and then the probability surfaces for each of the different classes. And then finally, the texture map displayed here as well. So those are hot off the press. I'm encouraged by them. I see some room for improvement. Our next steps will be, first of all, to sort of refine our technique using the Hearst area, include the vegetation, and then go through the true ensemble approach and testing the other approaches as well. Then we need to sort of repeat this whole process with our other two case study areas and do a comparison to see which of the approaches worked out best. And then identify gaps. And as you can see, it always comes down to how much data you have, the quality of that data. So that's where we are with the mapping phase of it. In terms of outcomes and outputs, I think that at the end we'll have a good suite of tools in our toolbox to help improve defining the soil data layers and refine the processes for creating that data, both for eFRI, but for many other users as well, whether it be specific forest licensing users or the communities in the area that want to know more about the soils, the First Nation communities, et cetera. I think there will be a lot of uptake for this type of information once it's available. So our plan is to do some knowledge and tech transfer to whoever is interested in terms of understanding what data is needed, how to use some of these techniques. Obviously, this isn't necessarily at a stage where it's just plug and play, that you can just sort of send out something to someone and they plug in their data and it spits out results. There is some knowledge required to tweak parameters and stuff like that. So it's not necessarily a plug and play thing at this point. And then we'll try and disseminate as much as we can, both to the academic literature, but also fact sheets to the forest industry community and forestry community at a large as well. So that's all I have for now. I'd be willing to take any questions now or over break if you have any insights for me or anything else that you would like to add. Just feel free to contact me and I'd love to chat more.
Does anyone have a question or two for the good doctor?
Why 42 soil texture classes? The last time I took Soils 101, I think there was 5 or 6.
Yeah, there was like, I think there was like 12 different types of organic matter breakdowns as well. So it was just, I think he took sort of the finest breakdown that they had in the literature. It's probably not reasonable to have 42. You're right. Yeah.
Did you, you said this was just a LiDAR approach, LiDAR data only? You didn't use the eFRI? Like, I'm just thinking about the inventory data itself where we had the polygons with ecosite calls.
Yeah, that's actually, I'd like to try and include that in the next.
Because I think that's been done, I think in BC or other places, but I'm just curious if
Yeah,
that's...
that would be helpful. So I'm at this stage, I'm looking to see what other things, and I think that one in particular would be really useful to add to it. Yeah.
Okay, thanks.
Yeah. In terms of the comparison, I know at one point there was talk about GeoSAR as being the DEM of choice. I'd like to still try and do some comparisons between the OBM, DEM, LiDAR, and maybe GeoSAR to see to what degree do we really, what resolution is ideal? Can we get comparable results at resolutions that are coarser as well? So that wasn't necessarily part of this project, but I think it's something that would be valuable to do as well.
So as for your machine learning learners, you used the random forest and you ended up using 2 variables in your model, right? So how did you end up using 2 variables instead of 3 or 4 or more?
So,
does that increase the accuracy or by incorporating other variables or?
So we use 25 different topographic indices from the DEM, and then we use the surficial and bedrock geology. So there was more than 2 variables in it.
I saw other categories in your previous slides, right?
For the moisture?
Yeah, something like that.
Yeah, so there was nine categories for moisture.
And are there other variables to increase the accuracy?
Well, so what I want to do is I want to try and include at least a vegetation layer and whatever additional maybe eFRI interpreted layers that could potentially go into this as well. So this is really sort of a first cut. It's still pretty kind of a crude start to it, but yes, we want to try and include more layers that we can. Do you have some suggestions of things that I should include? I'm open for suggestions.
No. And for your sample locations, you said you picked 3 locations in Southern Ontario.
As of right now, we're just concentrating more on the northern
So does it
Ontario.
mean your model is not applicable to Northern Ontario or other provinces?
This approach has been used, so Brandon did his PhD at UBC, so he's used this approach in BC before. He's now in Nova Scotia. He's planning to use this approach in Nova Scotia as well. So it's been tested quite widely for different projects in British Columbia.
Okay, it's very interesting project. I just had maybe a little bit same type of technical question regarding to the random forest. Just wondering, you use some samples to train the random forest model and use some samples to validate the prediction. And what is the percentage of training and validation samples? And do you think if there were different percentage would be change the prediction accuracy in the end?
So there was 70% that were used to train, 30% to validate, and then it was repeated using like a bootstrap method 50 times.
And
It was resampled.
is there a particular reason that you choose 70% instead of use 75, 80%?
That was just what had been used, Brandon had used previously, and he had found that to work well. But that's something I think that you can sort of easily play with to see if there's an optimal.
Okay, so I just had a second question is about the resolution of your mapping product. You said it's about 10 meters, and I was kind of wondering if the user want to use mapping for wider or different spatial scale for different applications. Let's say if the user want to have a mapping of about 1 meter, or user want to have a mapping about 50 meter, 100 meters. Is this tool gonna consider this situation, or it's gonna stick at the 10 meters in the end?
Well, it's a good question. I mean, part of it that I would like to investigate is how coarsening, for example, coarsening the DEM would affect your predictions. I think that's something that's important to try. In my experience, somewhere between 2.5 and 10 meters for most soil properties is reasonable. If you get below 2.5 meters, you're just dealing with a lot of noise. So most soil processes, can be represented over scales of, say, 2.5 to 10 meters. And so that's, I would say, optimal. You get too coarser resolution than that, then you lose a lot of the processes that are occurring at a smaller scale. When you get too fine, then you're just dealing with noise all the time. So.
Thank you. We have an emailed question from Krish Homigan of M&R Timmins. Can anyone answer me who is using LiDAR information data on Hearst Forest? I heard that LiDAR was available for Hearst Forest in Ontario.
Yes, so this LiDAR was from the Hearst Forest. Yeah. So this is LiDAR for Hearst. Yeah.
One more last one down here.
My question is, how do you compare, for example, this product versus the wet areas mapping work that's being done out of UMB and has been done in Alberta? And do you think that approach would lend something to your work?
Yeah, so wet areas mapping could be used as a layer in this. It is all DEM based in terms of its interpretation. The one that I pointed to here, a different approach that I've used for wetlands is a stochastic wetland mapping approach, but also uses the LiDAR DEM. If that layer was available, then I think that would, it could be something that you could include. Currently, it's not something that you can do easily without having someone from Paul Arp's group actually do it for you, whereas the stochastic wetland approach is something that isn't really proprietary, so to speak. It's an open source approach to mapping wetlands. So, but yeah, it would definitely be a good layer to have. Even if it wasn't used necessarily to go in, it could be used as sort of a validation type, external validation approach. Yeah.
With that, I think we'll wind up this particular presentation. Dr. Webster, the questions suggest there's a lot of interest in this. We can do nothing, say, keep going, girl. And congratulations on the personal side of this whole thing. That's very good.